Hey, welcome back. We've got proteins and nucleic acids left to talk about. We're going to start with proteins. I have simplified this as much as I can, made it as few slides as possible and as few vocabulary terms as possible. So what I want you to know about proteins is that first, they are a polymer made out of amino acids, of which there are 20, but I'm never going to ask you that. You can see the basic structure. Here's one amino acid. Here's another amino acid. I'm never going to ask you to identify the structure of an amino acid. I just want you to be familiar with it. They all get linked together like this. And if you look here where the R's are, the R is whatever is bonded to that carbon right there that would make amino acid 1 different from amino acid 2. So that's what makes each amino acid different, is what we call the R group. This gives it physical and structural properties. So some amino acids are big, some are small, some have charge, some don't. And collectively, because they're all different, they give each protein different shape, different chemical properties, different physical properties. Proteins do a lot of things within your body. The analogy I usually use is that you want to think of them like metal. Right? Metal can be used for a lot of things. Right? Metal can be structural. It can be stiff. You can make a spring out of metal. It can be very flexible. You can hammer it into sheets. You can make whatever. You can do a lot of different things with metal. And it can also be mechanical, right? So your car engine and lots of things that have moving parts, those moving parts are often made out of metal. The moving parts that in your body are made out of protein, we are going to call enzymes. So these are the little protein machines that do a lot of the chemistry that needs to get done in your body. They either help the chemistry happen or they actually physically cause things to happen themselves, like a muscle contraction. All right, so the next thing I want you to know about proteins is that their shape is very important. Like if you just think a Phillips head screwdriver is shaped differently than a flathead screwdriver, or a screwdriver is different than a hammer, but they both have metal in them. They do different things, so they have different shapes. That's the way all proteins are. The fancy name for shape that we have in science is called conformation. So a protein will start out as just a series of amino acids. So theoretically, it's just a string. As those amino acids are being linked together, they interact with one another and start to fold up in different ways, almost kind of like how saran wrap or plastic wrap starts clinging to itself the second you take it off the roll. That's what amino acids do. They start folding back in on themselves and then making these more complex shapes. They fold up in a bunch of different ways. We're not going to get into it. There are different levels of structure. Who cares? You don't need to know. At the end of it all, if you have a series of amino acids all linked together, folded up into a shape that is functional, that final shape is called the conformation of that protein or polypeptide. Whoops. There we go. So proteins can lose their shape. When they lose their shape or lose their conformation, that is called denaturation, or a protein being denatured. When a protein is denatured, because it loses its shape, it also loses its function. Right? If you dull the edge on a knife, it doesn't work anymore. If you strip the grooves in your Phillips head screw, then you can't unscrew it. It doesn't work anymore. If you lose your structure, you lose your function. There are a couple of different ways in which proteins can be denatured. It's usually either by heat or a change in pH. Heat is just like we have here, boiling an egg, frying an egg, cooking a steak. If you subject a protein to heat, it's going to unfold, and that's going to change its, what's the word I'm looking for? It's going to change its conformation. It's not going to be able to do its job anymore. This is why we cook a lot of things, because it is protein that gives food structure. This is why you have to chew it in part. Yeah, even like a carbohydrate, something that you think of as a carbohydrate like bread, what's giving the bread the chewiness is gluten, which is a protein. If you cook a protein whose job it is to hold something together like a steak, and that protein starts to denature, then it's no longer holding all the fibers of muscle together in that steak, and after you cook it, it becomes a little bit more tender. Another way that proteins can be denatured is by being exposed to acids. A base can also denature a protein, but acids are better at it, and you don't need to know why. So if you add anything acidic to milk, it'll curdle. If anybody's ever had ceviche, this is usually small bits of seafood, whitefish, sometimes shrimp, with, I think, onions and some other stuff in it. I forget. I never made it. I just eat it. But all you do is you chop up fish into small pieces with whatever else you want to flavor it with, and then you add, I think it's lemon juice, not lime juice. It might be lime, doesn't matter. And the acid in the citrus, the citric acid, denatures the fish and essentially cooks it. So that's ceviche. Some of you have probably had it, some of you haven't. If you haven't, I highly recommend it. I'm not a big seafood person, but ceviche is quite delicious. All right, I mentioned enzymes, and we're going to talk about them briefly. So an enzyme is one of the things that a protein can function as. It's one of the shapes that your cells make proteins out of. And what enzymes do is catalyze reactions. As it says here, a catalyst speeds up a chemical reaction without being altered or consumed. An example from everyday life is the catalytic converter on your car. You may not know this, but your car has a catalytic converter in it. I believe it's got a lot of platinum in it, which is why people steal catalytic converters for that metal. But so what happens is as the exhaust fumes flow past that metal catalyzes some sort of reaction that then detoxifies, for lack of a better word, or sort of processes the exhaust so it's not as bad when it comes out your tailpipe. As long as your catalytic converter doesn't rust and fall off, it's good for the life of your car because it doesn't get consumed or altered. It just makes that reaction happen every time exhaust flows past it. And that's what enzymes do. So here they're just showing you have two small molecules. They interact with the enzyme. The enzyme makes it easier for them to join, so a bond is going to form, and then you end up with a product. This is how proteins are made. Amino acids linked together by an enzyme, which we call the ribosome. And it's also how glycogen is made. You take sugars, you link them together, you make a big molecule. There's another enzyme that can take apart the glycogens. It just does the reverse reaction. I just want to show you the importance of enzymes, and I may end up having to make a third video because I talk too much, but whatever. Each one of these little blue pieces of writing is the name of an enzyme that is making the reaction from this to this possible, or this reaction going from here to that, to this, to that. This all looks like steroid biochemistry. All that blue is an enzyme. All of that blue is a protein making sure that a chemical reaction happens when it's supposed to and where it's supposed to. And if you zoom out and look at this picture, you can see that your cellular biochemistry is bonkers crazy. And there's enzymes everywhere, really just sort of guiding all of the chemistry. we're going to stop there, and I'm going to make another short video, 5 to 10 minutes, just about amino acids, because I don't think I can make a video more than 15 minutes long without having to pay for this program.